Good morning, everyone. Yesterday, we had to quickly end the class because we were over time yesterday. So I'll continue from where we left off on the last date. And also, I hurried the last section a little bit, so we'll go through the same section again today. Let's wait for a couple of minutes for others to join.
पेपर की फोटो भेजी है।
Meantime, do you guys have any other question? Also, yeah, regarding the assignment, I told you guys submit in a single file, either PDF or image file, okay? Don't submit one file for one question. Combine all the answers and submit in a single file. Okay, let's start this class. So, yesterday we were discussing mainly about constraints and the degrees of freedom. So, we mainly discussed about these constraints. And we told you that the constraints are basically the conditions or the restriction that is imposed on the motion of a particle or a system of particles. That is, those are called constraints. Okay. And we also gave some examples of these constraints and degrees of freedom as well. So for example of constraints, we told you that for example that if some particle is
করে আমি খারাপ হয়ে যাই যে লোকেরা আমাকে খারাপ ভাবতে থাকে কেউ
and
একবার আমার জায়গায় এসে ভাববে
who is this? Don't make noise, otherwise I'll remove from class. So constraints are basically the conditions or restrictions. For example, we told you that let's say you have a sphere and one particle is restricted to move only on the surface of the sphere. If it is restricted to move only on the surface of a sphere, so that is one type of constraint. Or let's say there is that you have a car. So this is a road along x-axis, and you have a car. Let's say you have a car, and that car is restricted to move only along the x-axis. So that is also a constant. Ideally, this bus could move either x, y, z, any other direction, but we impose this restriction that it should move only along x direction. So that is constant, that is imposed on this motion of the particle or the motion of this bus. And the degrees of freedom, we told you that the independent coordinates that you require, degrees of freedom We told you number of independent coordinates. So this is very important. The number of independent, this two term is very important. Number of independent coordinates. This independent coordinates. So there can be dependence. So you have to remove those dependence and then then look into which coordinates are independent. So from there you will get the degrees of freedom. So number of independent coordinates that require to completely specify the dynamics of a system. Dynamics of particle or system of particle, that is called degrees of freedom. So we gave example let's for this example of this simple pendulum, that this pendulum has only one independent coordinates. This coordinate is theta. So it has only 1 degrees of freedom. So in this case, the degrees of freedom is 1. Okay. So what I want to do, so I want to give you few more examples before we continue. Okay. So first example that I want to take, let's see. So all of you know this problem of this inclined plane, right? So you have solved this problem of inclined plane many times in your class 12 exam. So let's say you have this inclined plane, okay, and you have a coin on this inclined plane, okay. Now this coin is moving on this inclined plane without, this is rotating. So this coin is rotating without any slipping on this inclined plane. So how many degrees of freedom this coin will have? Can you guys tell? So let's say this is your x-axis, this is your y-axis. So of course you can, anytime you can tell what is the position for this coin. You can tell xy coordinate for this coin. So, or if it is a 3-dimensional, you can tell. So let's keep it 2-dimensional. So we can always specify the center of this coin by xy coordinate. So can you guys tell how what is the degrees of freedom for this coin? How many degrees of freedom we have here?
2.
Sir, degrees of freedom is the angle that this ball or this object creates, right?
Angle with what?
With the surface, like ऐसे नीचे की तरफ एक एंगल बनेगा और एक इस तरफ बनेगा, तो 2 एंगल्स होंगे, तो 2 डिग्री ऑफ फ्रीडम.
2 degrees of freedom or 1 degrees of freedom? How much? So what you are telling that this is the angle theta. This is the angle, right?
Yes, sir.
Then how many degrees of freedom we have here?
1.
Any other answer? How many degrees of freedom we should have?
2.
Two, sir.
So some of you said 1, some of you said 2. Which one is correct? Why we should have 1 degrees of freedom here? Can you explain? So I told you this is rotating. This is rotating means so this is also moving along this inclined plane, right?
Yes, sir.
So then we should have 2 degrees of freedom or 1 degrees of freedom. So your answer is correct. It will have 1 degrees of freedom because let's say this started from this point, okay, this top of this inclined plane, okay. But if you know the angle theta, so then you can tell what is the position. Let's say its radius is a, okay. So if you know the angle and if you know the radius of this coin or the cylinder, then by multiplying a with this angle a and theta, you can tell how far it has moved. So you don't need to independently know the position, how far it is moved from this position, right? So that is related to the what is the angle with respect to this coordinate or the starting position. So these two are not independent. So your answer is correct that this has only 1 degrees of freedom. Okay. Now, let's change this problem little bit. So this coin not only can rotate, but it can also slip. Okay. This can also slip. Okay. Then how many degrees of freedom we'll have here? So rotation means, you guys understand the difference between rotation or slipping. So rotation means the point of contact, there is no velocity. But slipping means the point of contact can also has some velocity. It can slip along some direction. So in the first case, I told you that there is no slipping. So this coin only rotates. But now I am telling that this coin can slip, but it can also rotate. Then how many degrees of freedom we'll have in this case? Any answer? So let's say this coin started from this point and then it's rotating as well as this coin is slipping down this inclined plane.
2.
2.
Yes, then we'll have 2 degrees of freedom, because then this distance and this angle, then these are not correlated, right? Because when it is slipping, then it's may be rotating, it may not be rotating. So the distance this coin is covering, that is much more than the angle it is rotating. So these two are then independent. So you need at least 2 coordinates. So you have 2 degrees of freedom. Okay, let's take
Sir, can you please repeat the part where the coin is rotating?
what?
Can you please repeat the part where coin is rotating?
So if the coin only rotates, then the angle and the distance, these are related, right? Like, so forget about this inclined plane. This is a plane straight line, okay? So this is your coin, okay? And if this coin is only rotates, so how much distance this coin covers, it is related to this angle, right? This angle theta. This angle theta and the radius of the coin A. So if you multiply radius with the angle, you will get how much distance it has covered. But when it starts
Sir,
slipping also, then you
excuse
cannot
me,
tell it.
sir.
Yes,
Sir, could you please explain it in Hindi?
I'm not very good in Hindi.
It's okay, sir, we'll manage.
Uh, he- what I'm telling you guys, that there's 2 different motion. One is only rotating. Rotating means that this disc will only rotate. It will rotate only along about this axis, this center axis. Slipping means, let's say you push this coin from this side. Okay, we push this coin from this side with some force here. Okay, so what will happen? Then this coin will move along this x-axis. It don't need to be don't has to be rotating. Okay, so in that case, this angle is not related to to the distance it is covered.
Sir, if it is slipping, then angle should be related to the distance.
No, if it is sleeping, then it's
Sir,
don't
if
need
it
to be
is slipping,
related.
then no angle movement would be there.
If
So
it can rotate, so there's two. I'm saying 2 movement. One is rotating without sleeping. This is one movement, and second movement is rotating and sleeping. Okay. In the first case, you have degrees of freedom 1, because it is related. Angle and the distance are related. But in the second case, angle and the distance are not related. That's why you have 2 degrees of freedom. Okay. Let's quickly take another example, that you have some arbitrary path. Okay. This is one arbitrary, this is x and y axis. This is one arbitrary path. And you have one ball of mass m. It is following this path and moving along this path. Then how many degrees of freedom we have here?
Two,
Two.
sir.
Why 2?
One angle and
Mhm. So this path is, let's say this is a road, let's say this is a predefined path, okay? This is a predefined curve, okay?
three, sir.
This
So
is
one.
a predefined curve.
So one.
Like this example I told you, let's say this is, instead of curve, let's say this is a road, okay? This is a road, and you have a car. That car is moving along this road. Then how many degrees of freedom we have here?
One, sir.
You have 1 degrees of freedom because this path is predefined. So at if there is a relation between x and y coordinate. If I give you the point x, you can tell where this bus will be. The point y is known in this case. If this path was not there, then you would have 2 degrees of freedom. But this path is
Like we
already
have
there. So
equation.
there is a relation between x and y. So that's why you have 1 degrees of freedom. Okay.
We have equation of this path.
Yes, you can write down equation. You can write down equation. You can make a chart and so and know the position y in terms of the coordinate x. Okay. Okay. Last one I want to tell you about the rigid body. So let's say you have this cube made out of iron. Let's say, okay, this is a cube and this is made out of iron. Okay, let's say. So this will be a rigid body, right? Then how many degrees of freedom this body has? Let's say this is in a 3-dimensional space, x, y, z. It is sitting somewhere. Then how many degrees of freedom we have for this rigid body?
Three. Three, sir.
3. Any other answer other than 3?
Sir, if it is rigid, then only three. If not, then it can be more.
So you guys are telling 3 because it can move along x, it can move along y, it can move along z direction, right? That's why you guys are telling 3. But if this is a rigid body, it can also rotate. Let's say this body, this can rotate either around x-axis, around y-axis, around z-axis. So this body can rotate as well. So it has 3 degrees of freedom for translational motion.
6, sir.
And you have another 3 degrees of freedom for rotational motion. So you have in total degrees of freedom is 6 in this case, okay? It is, so you have to consider both the rotational as well as the translational motion here for this rigid body. Okay, so you guys should practice. If there are many, if you search in internet, there will be many examples. Okay, you guys should search and solve some problems. Then you will be more familiar with how many this constant and the degrees of freedom. And I want to also write down again this classification that we started in the last class. Classification. So I told you there is you can classify 4 ways. So one, I told you that this can be either holonomic or non-holonomic. Holonomic means that you can write down the constant equation. So what is a constant equation? So constant equation is like this case of simple pendulum. Let's say this is the simple pendulum. So in this case, what is the constant equation? That root over x square plus y square, this is equals to L, the length of this pendulum. Or if you let's say this is a gas filled sphere, this is a gas filled sphere and this radius is A. then the position of any particle at any time must be less than A. So these are constant relation, okay. So in case of holonomic, this constant relation, they depends only on the coordinate. They depend only on the coordinate, and they form a equation. They form a equation in case of holonomic constant. But in case of non-holonomic, they can also depend on velocity. And they can also be inequalities. So those are non-holonomic constant. Okay. For example, this example of this gas filled sphere. So in this case, the constant is in the form of a inequality. So this is a non-holonomic constant. Okay. So second, I told you that it can be scleronomic or rheonomic. So in this case, this is independent of time. The constant relation that we have written, that is independent of time. But in this case, it depends on time. Can you guys come up with an example where the constant relation depends on time?
Y equal to X times.
So let's see this familiar example of this case, this simple pendulum. Okay. So in this case, this simple pendulum, okay, this is angle theta. Okay. So we told you that this length L is fixed. Okay. That's why it was scleronomic constant, that is independent of time. Okay. Now let's say this hook position, where it is suspended from, this position also moves along this axis, x or y, this along plus x or minus x direction. Then to know the position of this pendulum, then you need to know the constant relation in terms of the time, because then this position is time dependent. So this will be a rheonomic constant. Or let's say people say let's say you have a wire and you have some beads around on the wire. Okay, this is a wire. Okay. Now, if the wire is not moving, then this is a scleronomic constant. This bead can move either along x or plus x or minus x direction. But if this wire itself is moving along x or plus x or minus x direction, then this bead can move also plus x or minus x direction. But because this wire is again moving, so this constant is again time dependent. So this is again a rheonomic constant. Okay. So third one that we told you, that conservative or dissipative system. So in case of conservative, that the constant forces, they do not do any work and the total energy is conserved. In case of conservative constant, these forces of constant, they do not do any work. So total mechanical energy is conserved. But for example, in this case of pendulum, here the constant force is basically the tension in the wire, that wire, so that balances the gravitational pull. So that is a conservative force. But dissipative force, for example, if you have a frictional force, there that will do some work, and that will be an example of dissipative constant. And fourth type that we told you, that bilateral and unilateral. So this is a little bit hard to understand. So bilateral is similar to holonomic constant, that it will form an equation. Okay, it will form an equation, but in case of holonomic, we told you that it only involves the coordinate of the particles or the system of particles. But in case of bilateral, it does not matter. it can include velocity, angle, anything. Okay. But unilateral, they are again inequalities. Okay. So bilateral basically means it allows motion on the both the direction. But unilateral means it restricts the movement along certain directions. Okay. So one example is there in my note. If you see this gas filled sphere, their gas molecules are not allowed to go outside this sphere. So so movement is restricted at a certain point. Movement is restricted along a particular direction. So that's why that is a unilateral constant. Another example is that this swinging door you have. Okay. So in case of swinging door, let's say you can only open the door from the certain point. You cannot close it. So that will be one example of unilateral constant. I'll give you some more problems to work out. So if you do this, apply these rules to many problems, then you will be more familiar. But so what we can do, that we can ask you that if we will give you a system and then tell you to classify the type of constant that is involved in that case. For example of this rigid body. So we can ask you that, okay, you have a rigid body, then you classify the type of constant in the rigid body in terms of these four classification methods. Okay. So for example, in this case of rigid body, so you can say in case of rigid body, this will be a holonomic constant. The constant will be holonomic because the rigid body relation is basically Ri minus Rj, that is equal to Cij square. That the distance between two particles is always constant. So that is a holonomic constant. Okay, holonomic constant. And this is also does not depend on time. So this is scleronomic. So here the forces of constant do not do any work. So this is also conservative. And this is also works on both ways. So this is a bilateral. So we can give you a system, and then we'll tell you that you classify that constant in the system accordingly. Okay. So there are many examples available. You guys should practice. You guys should take up some example and then practice this to find out the type of constant you have. Okay. Now I want to move on to another topic that is called generalized coordinate. Generalized coordinates. So what is generalized coordinate is that we have already studied that defined coordinate system, right? That we have Cartesian coordinate, we have plane polar coordinate, spherical polar coordinate, and those are basically that we choose those coordinate system based on the symmetry of the problem. That in a particular problem set, maybe one type of coordinate system is more useful or it is easier to handle. For example, if you have a you have a problem involving sphere, so in that case, if you apply the spherical polar coordinate, then it will be easier for you to handle the problem set. So that depends on the symmetry. That choice of coordinate system is basically governed by the symmetry of the problem. Okay. But generalized coordinate is basically to minimize the need of the number of independent coordinates. For example, of this case of simple pendulum, let's go back here again. Okay, so here we can choose XY coordinate system, right? We can always choose X and Y coordinate system and solve this problem. It should not be any problem. Okay, but instead of X and Y are related. So we know here this is the relation X square plus Y square equal to L, this length for any time. So we can see X and Y are related. So we don't need this two coordinate system to solve this problem. So here only the independent coordinate is theta. So if we have this only one coordinate variable, then it is sufficient to completely describe this system. So here theta is called generalized coordinate. This is called the generalized coordinate here. I can give you another example that let's say you have one spring, it's attached, and one mass is attached to the spring. Okay, mass m. Okay, and this mass can move along x direction. Okay. Now you can set up you can set up a xy coordinate system here and specify this position of this mass in terms of x and y coordinate, and then take that the mass is moving along x direction and then solve the x and y coordinate system problem. But we here really don't need the y coordinate system. We only need to know that what is the distance of this mass m from this rigid support. So that is the only one coordinate variable that you need here. So here x is, and that is the distance x. And here x is the generalized coordinate. That is the generalized coordinate. So in terms of definition, what you can tell that these are the set of independent parameters. So you can give a definition that this is the set of independent parameters that gives complete description, complete representation of the system. So you can see this is similar to the degrees of freedom. In case of degrees of freedom, we have seen how degrees of freedom is basically how many independent variable you need. That number is the degrees of freedom. But generalized coordinates are the variables. The variables that you need, those are the generalized coordinates. And you can see that this number of generalized coordinate, this should be equal to the number of degrees of freedom. For example, in this case, degrees of freedom is 1. And you have only one generalized coordinate. Okay. Here again, you have only 1 degrees of freedom. So you need only one generalized coordinate. If we take that another example that we have, let's say one mass is hanging from here, and then you have another mass m1 and m2 hanging from here. Okay, this angle is θ1, and we told you this angle is θ2. So in this case, we have degrees of freedom equal to 2. And what are the generalized coordinates here? So generalized coordinates are θ1 and θ2. So these are called generalized coordinates. Now, in general, if you have n number of particles, if you have n number of particles in a 3-dimensional space, in 3D space, so if there is no constant, on the motion of this n number of particles, so you will have 3n degrees of freedom. You have 3n degrees of freedom. But let's say let's consider k number of constant. So then your number of degrees of freedom will be 3n minus k. Okay. And how many generalized coordinate you will need in that case? So generalized coordinate, so those will be also, their number will also be 3n minus k. And this is applied for holonomic system. Okay. For non-holonomic system, that is little bit complicated. We'll not go there. Non-holonomic constant, they can reduce the degrees of freedom, but that is not necessary. In some cases, they will not reduce the degrees of freedom in case of non-holonomic constant. So only if this constant are holonomic, then it will decrease the number of degrees of freedom by that amount. And this generalized coordinate, they are represented by this variable q1 or qj. Okay, those are represented by qj. So, and you can build a relation between the real coordinate, this normal coordinate system, which we say in terms of the position vector r, and this is the general coordinate system. This is the Cartesian coordinate system, right? We can write any vector r, position vector r, equal to xi cap plus yj cap plus zk cap. But the generalized coordinate, those are represented by qj. So if you have n number of generalized coordinate, then you can write the generalized coordinates are q1, q2, q3, dot 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 qn. So if you have n number of generalized coordinates, you can write like this. And there is always relation between this Cartesian coordinate system or the old coordinate system that we knew so far, either Cartesian system or the polar coordinate system or the spherical polar coordinate system. So there is always relation between this old coordinate system and this new generalized coordinate system. So you can write one in terms of the other. So generally, so what we are telling you that let's say R1 is the position vector, so that you can express in terms of generalized coordinate q1, q2, q3. And let's say there is 3n number of minus k degrees of freedom. So you can write this. Okay. You can R2, so you can write R2 equal to q again q1, q2 dot dot qn 3n minus k t. And you can write for all this. If you have Rn, you can write Rn q1, q2. Can you guys tell why we're writing up to n here? I told you that for n number of particles, we'll have 3n degrees of freedom. So why we're writing only n number of position vectors? Anyone? Do you guys understood what we are discussing? I need your response, whether you guys understood or not. Okay.
Yes.
Can you tell why we are writing Rn? I told you that if you have n number of particles, there will be 3n degrees of freedom. So why we write R1 up to Rn? Why not R3n? You can see I wrote that if you have n number of particles, degrees of freedom is 3n minus k, because there is k number of constant. So you have 3n minus k generalized coordinate. Okay. And this can also depend on time. So we wrote time also. But for the position vector, I wrote only up to Rn. Why?
Because there is only n particle and we are writing position vector for the particle only.
So each position vector, they includes 3 degrees of freedom, because position vector, that is xi cap plus yj cap plus z cap. So you can see there is 3 variable already there for 3 degrees of freedom. So whether it is Rn, but the number of degrees of freedom, this includes 3n. Okay. But these R1 to Rn, they are not independent. Okay. R vectors, Ri vectors, they are not independent. They are not independent. Okay. But
Yes, sir. They are dependent on 3n minus k coordinate system.
Qj they are not independent. But Qj vector, they are independent of each other, not independent of each other. But they are here Qj are independent of each other. Can you guys tell why I'm making this statement? That why Ri, these position vectors, they are not independent of each other. But Qj, which are the generalized coordinate, they are independent of each other. Can you guys tell why I'm making this statement? Ri is the position vector in the Cartesian coordinate system, and we have a number of constant. Okay, so what is constant? Constant basically they relate this coordinate variable. That's why those are, we have this constant. For example, of this case of double pendulum. Okay, this double pendulum case. Okay, what are the RIs you need in this case? M1, M2. What are the position vectors you need if you represent this in case of XY coordinate system? So you need firstly you need the position vector R1 for the mass M1, which will be either you can write in terms of X1 and Y1, right? And for the mass M2 you can write in terms of X2 and Y2. But R1 and R2 are related. They are not independent. Here X1, Y1, X2, Y2, they are not in, all of them are not independent. They are related. That's why we have 2 degrees of freedom here. That's why you have 2 degrees of freedom. But this generalized coordinate, what are the generalized coordinate here? This is θ1 and this is θ2. These two are the generalized coordinate. So here QJs, these are θ1 and θ2. These θ1 and θ2 are fully independent. θ2 does not depend on θ1. Okay. So this generalized coordinate, they are independent of each other. But this whole position vectors, they are not independent of each other. If there are some constant, this position vectors are not independent of each other. Okay. So that is one benefit of using generalized coordinate, that all the generalized coordinates, they are independent. Okay. Is this point clear to everyone?
Yes, sir.
That is one of the and that's why that is the reason that we can reduce the number of coordinates. As I told you, for n number of particles, we have 3n degrees of freedom. So how many position variables we need in this case? So you need x1, y1, z1, x2, y2, z2, and so on, right? X, n, yn, zn. So these many position variables you need for if there is n number of particles and you have 3n degrees of freedom. Now if you impose k number of constant, so number of degrees of freedom will be Tn minus k. So as soon as you impose this condition, that if you reduce the degrees of freedom, you will find out that these coordinates are not independent. There will be some relation will exist between these variables, these x, y, and z variables. Okay. And that's why you will have reduced number of degrees of freedom. But when you represent this system again in terms of generalized coordinate, q1, q2, q3n minus k, these are all independent of each other. Okay. Now, so we can write, let's say we can write Ri. This is a function of the generalized coordinate q1, q2, q3, let's say q3n t. Okay. So if we want to find out the velocity, what we can do. So velocity is basically dri by dt. Okay. So what we can write then, this we can do partial derivative, that del ri by, these are function of qj's. So this summation will run from j equal to 1 to 3n. It runs for all the generalized coordinates, and this will be qj dot plus del ri del t. What is qj dot? Qj dot is basically dqj dt. Okay. This is clear to everyone why we are writing this? That if Ri is a function of this generalized coordinates q1, q2, q3, we can write this velocity like this: dri by dt. This will be a function. So you can do partial derivative in terms of this generalized coordinate del ri del qj, and also partial derivative with respect to time. This differentiation is clear to everyone. If you guys have any doubts regarding this differentiation, you guys can tell me, okay? Otherwise, it will be difficult for you to derive. If we ask you to do any derivation during exam, it will be difficult for you. You cannot memorize all this differentiation. Okay. So you should really understand how this differentiation works and why we are writing like this here. So here what we wrote qj dot because dri by dt, there is also del t term, and that came here del qj del t. So that's why we wrote qj dot. Okay. Or you can also write this is ri dot in terms of j del ri del qj dot plus del ri del t. And what is qj dot? Qj dot is called the generalized velocity. This is called generalized velocity. Okay. So if we know the generalized velocity, you guys should find out what will be the kinetic energy. Okay. You guys should find out what will be the kinetic energy. This you should do as a homework and find out that we can write mi ri dot square, right? The kinetic energy. Then what is ri dot? Ri dot we wrote what this is ri dot, right? So we can replace mi. This will be j del ri del qj dot plus del ri del t dot. This is ri dot square, so you have to open another bracket. This will be k, let's say del ri del qk dot plus del ri del t. So what I have changed the index, only this qj index I have changed. In the first case I kept it j index, and second case I changed it to k. Okay, these are just the dummy index. These are okay. So you guys should find out the expression for the kinetic energy using this. Can you guys do this at home, or can you guys try? Everyone, can you guys tell me whether you can do this or not? Whether you guys understood what we wrote here? Okay, if you guys are not responding, then it's up to you whether you understood or not. So, but you guys should finish. You guys should finish this. What will be the expression as a homework? Okay. I want to introduce another concept called virtual displacement. Okay. Virtual displacement. So we are familiar with real displacement. That let's say you have a particle of mass m here. Okay, this is say x, this is say x, y, and z coordinate. Okay, and this is the position Ri. Okay. Now, how you can displace this particle? You can displace along any direction, x, y, z, any direction, and let's say, and then it will have a new position vector, right? It will have a new position vector Ri prime, let's say, and old one is Ri. And this real displacement, this is a real displacement. This is a real displacement. And this is generally we represented by dRi. Okay. This is we replace by d, we denote it by dRi. Now for real displacement, if you are moving the particle from 1 to 2, okay, so you need some amount of time. Okay, you need some amount of time to move the particle from 1 to 2 in case of real displacement. What is virtual displacement? So virtual displacement, that is represent that virtual displacement is represent and instantaneous. Okay, instantaneous change in the configuration of the system, which is consistent with the forces and constraints on the system. So here two terms is very important. One is this is the virtual displacement, or let's say this is a virtual infinitesimal. We are always talking about infinitesimal displacement. Okay, infinitesimal means very small displacement. Okay, here this term is very important, that this displacement is instantaneous. Now, in case of a real displacement, can you guys imagine where we can have instantaneous displacement, that you move this particle from 1 to 2 without without spending any time? Is it possible? Is it possible or not?
No, sir.
No, sir.
Other guys? So in case of real displacement, you need some time to move the particle from point 1 to point 2. But here we are talking about virtual displacement, which happen instantaneously. Okay, but they will obey all the laws, all the forces or the constant that you have on the system, and those are represented by delta Ri. Okay, you need to be careful with this symbol now. Okay, this symbol, this delta Ri, this represent virtual displacement. Okay, you need to be careful from now onwards. That delta Ri, this is virtual displacement. Okay, and if we write dRi, this is real displacement. Okay. Okay. So this virtual displacement, this is just a imaginary concept. Okay. This is just a mathematical description. In reality, it's not possible. You cannot displace a particle from point 1 to point 2 without spending any time. So this is a purely imaginary concept, purely mathematical concept. Okay. But we will see in the next class that this will lead to some important conclusion and also development of a new kind of mechanics by using this concept of virtual displacement. And we will discuss little bit more on the virtual displacement in the next class again. Okay. Do you guys have any questions so far on this one? Any question? Do you guys able to understand so far what we are discussing from these degrees of freedom and onwards? Or you are
Yes, sir.
facing any difficulty? Okay, if there is no other question, nothing, then okay, let's end it here today. Tomorrow we'll discuss again this in virtual displacement. We'll continue from this. Okay. Okay, who is little difficult? You need to tell me what is the difficulty. Okay.
So,
Yes.
so regarding the practice of problems
Hmm.
for the current content you are teaching,
Hmm.
so in the book, what chapter we have to
This is chapter 1.
continue?
Chapter
Okay, so
1.
from chapter 1 only we have to start.
Yes. Okay, then let's end it here. We will discuss, continue from the virtual displacement again tomorrow. Okay. Okay. We'll see
Thank
again
you, sir.
tomorrow.